Hello and welcome to a new video on IGCSE Physics Paper 4. In this video, we shall be discussing speed-time graphs. An astronaut on the moon drops a feather from rest off the top of a small cliff. The acceleration due to gravity on the moon is 1.6 meters per second squared. There is no air on the moon. The feather falls for 4.5 seconds before it hits the ground. Draw the speed time graph for the falling feather. So let's check the answer here. In this case, the acceleration is 1.6 and it's constant. More important than the value is that it's constant. So we expect the shape of the graph to be linear. You should watch the concept video before watching this video in order to understand when the graph is linear and when it is a curve. In order to get numerical values, we're going to use the equation of motion that says V equals U plus AT. V is the final speed, U is the initial speed. So let me write this down. So V is the final speed here. U would be the initial speed. Of course, A is the acceleration and T is the time. So we want to get the final speed, and we know that it is dropped from rest. So from rest is a keyword here, and it tells us that U is 0, the initial speed is 0. And the acceleration is 1.6, and the time is 4.5 seconds. So all we have to do is multiply 1.6 times 4.5, and we get the final speed of 7.2. So when the time is 4.5, the speed is 7.2. Therefore, we have this point on the graph here, 4.5 and 7.2. Of course, you have to count the squares very carefully to make sure that here this is 4.5, and on the y-axis, this would be 7.2. After getting this point here, all you have to do is join 0, 0 with this point, and you obtain the graph shown. And this would be the solution to AI. In double I, we are told determine the distance fallen by the feather. So the new concept here that you should know is that for speed time graphs, the distance is the area. And let me give you a brief summary of how to remember what the slope is and what the area is and so on. So imagine that you have three brothers, A, V, and X, living in three different levels or stories in the same building. So A lives on the first floor, V lives on the second floor, and X lives on the third floor, for example. And to go from A to V, you take the stairs. To go from V to X, you take the stairs as well. To go from X to V, you take the slide, and from V to A, you take the slide. So moving down, we take the blue arrow here, which is the slide, and moving up, you take the stairs. This is just an analogy. It's like a metaphor in sense, just to help you remember what to do in each case. So if you're moving up, you're getting the area under the graph. And if you're moving down, you're getting the slope of the graph. So for example, in this case, in this question here, the graph is a speed time graph. So the speed time graph tells us that we are starting at V. And we are required to get the distance fallen by the feather. So to get the distance, we want to go to X. So X lives on an upper floor. So you have to memorize that A is the bottom floor, followed by V, followed by X. So to go from V to X, we're moving one floor up. So therefore, we have to get the area on under the graph. So how do we get the area here? Using simple geometry, of course. The graph here is a triangle in a sense. So the base of the triangle is basically the value of the time, which is 4.5, this value here, 4.5. And the height of the triangle is 7.2. So the area of the triangle is half times base times height. And all you have to do is simply multiply half times 4.5 times 7.2, and you get 16 meters for the distance. Finally, in question B, we are required to sketch the shape of a speed-time graph for the same feather falling on Earth. So how would that be different? The idea is that there is a keyword that we did not really pay attention to so far, which is that there is no air on the moon. There is no atmosphere, there is no air. So therefore, since there is no air, there is no air resistance as well. So this is why the acceleration is constant on the moon. However, on Earth, even though sometimes we are told, we just assume that the acceleration due to gravity is equal to 10, for example, this is not very accurate because in fact, in reality, there is air resistance on Earth because there is an atmosphere. So since there is air resistance, the acceleration is not constant. The acceleration is actually decreasing because while an object is falling due to the weight, it is faced by air resistance, a resistive force due to air. So therefore, what's going to happen is that the acceleration is going to decrease. And we know that the acceleration is the slope of the speed time graph. So we are looking for decreasing slope. And again, from the previous video on concepts, we know that decreasing slope looks something like a frowning face, part of a frowning face. So the curve is concave down like this. This is why, in this case, we are going to draw the graph looking like this. Anyway, moving on. A diver in the sea uses breathing apparatus which releases gas bubbles. Figure 1.1 shows bubbles rising to the surface. The bubbles start from rest, and at first they move upwards with a constant acceleration. Figure 1.2 is an incomplete speed time graph for one of the bubbles from t equals 0 until t equals 10. Using figure 1.2, determine the acceleration of the bubble during the first 2 seconds. So again, like we said, we have 3 brothers, A, V, and X. And we know that moving down, this is like the slide. We said this is like a slide, and this is equal to slope. So if we're moving down, we're getting the slope. If we're moving up the staircase, we are getting the area. And we always start at the letter that corresponds to the graph. And this is a speed time graph here. So we're going to start at V. Now, we are required to determine the acceleration. So we are required to go to A. So we're moving down, so we're getting the slope. So in other words, here, determine the slope of the graph or the gradient of the graph during the first 2 seconds. How would we determine the gradient of the graph? Using 2 points on the graph. So this here is 0, 0, for example. And this here would be 2, 0.5. So in order to get the slope, all you have to do is y2 minus y1 over x2 minus x1. Of course, this would be x1, this would be y1, and here you have x2 and y2. So you get 0.5 minus 0 over 2 minus 0, and that gives you 0.25. Therefore, the acceleration in this case would be 0.25 meters per second squared. So after t equals 2, the acceleration of this bubble decreases gradually until at t equals 10, its acceleration is 0. Complete figure 1.2 by sketching a possible continuation of the speed time graph. So like we said in A, the acceleration is the slope. So we want a decreasing slope. So the slope has to decrease, and we just said in the previous problem that this looks something like a frowning face. And then the acceleration is 0 at t equals 10. So we want at 10, the slope to be a horizontal line in a sense. So it needs to sort of plateau. We say this is a plateau where the acceleration decreases until it reaches zero and the slope is zero. So the line is horizontal. So the graph is going to look something like this. Let's look at the answer now. So like we said, we have a decreasing curve. And then around 10, this should be a horizontal line to represent zero acceleration. Finally, in BII, we are required to state a name given to negative acceleration, and this would be deceleration. A bus is traveling between points A and D. There are bus stops at A, B, C, and D, but the bus does not stop at B and C. Figure 1.1 is a speed time graph for the bus. The average speed of the bus between A and D is 23 kilometers per hour. Calculate the distance between A and D. So in order to calculate the distance, you should know that distance over time is equal to average speed. So average speed equals total distance over total time. Now, the average speed here is 23. So we can write 23 equals the total distance. And this is what we're required to calculate. Let's call it x over the total time taken to go from A to D, which is 2 minutes. So the problem here is that the speed is given in kilometers per hour and the time is given in minutes. So of course we need to convert the time from minutes to hours. So 2 becomes 2 divided by 60 in order to get the time in hours. And this would be something like 0.0333 or whatever. So therefore, 23 equals x over 0.0333, and we can get the total distance accordingly. Let's look at the written answer. Like we said, all we have to do is write 23 equals x over 0.0333, and we multiply the two together because we take this to the other side, and it becomes 0.77 kilometers. The bus stops at D for 1 minute and then travels at a constant acceleration for 30 seconds. On figure 1.1, sketch a possible graph for this additional motion. Label X when the bus starts to accelerate and label Y for 30 seconds later. So it stops for a minute, stops at D for 1 minute, and therefore the speed is 0. So for 1 whole minute, we have 0 speed from 2 to 3. And then it starts to accelerate at this point here, which is point X. So since the acceleration is constant, so we know that the slope is constant. And slope is constant means that the graph is a line like this. So therefore, we draw a diagonal line for half a minute, which is halfway between 3 and 4. And we label this point Y, and this would cover the requirements of the question. A lift or elevator starts from rest at the ground floor of a building. Figure 1.2 is the speed time graph for the motion of the lift to the top floor of the building. Use the graph to determine the distance from the ground floor to the top floor of the building. So we are required to find the distance using the graph, and we have a speed time graph. If you remember the 3 letters, we want to go from V to X. So we're going to take the stairs because we're moving up. And this tells us that we are required to get the area under the graph. So this becomes a geometry problem right now. The area under the graph, which is a trapezoid, is represented by half B1 plus B2 times height. What are B1 and B2? B1 and B2 are the parallel sides of the trapezium, which are this side here. And so let's call this B1, for example. And then the side above would be base 2. And we can get base 2 simply by subtracting the x value of this point here. Let's say x1, y1, minus the x value of this point here. So B2 would simply be x1 minus x2. So let's look at the numerical answer and see this together. So like we said, we have the area under the trapezium, and we got the x values of the 2 points. So the value of this point here is 20, and the value of this point here is 7.5. And the purpose of drawing these vertical lines is just to get the exact x value. So if you can see here, we have a vertical line, and this tells us that the x value is 20. We also have a vertical line here, and it's exactly in the middle between 5 and 10. So this tells us that the value here is 7.5, which helps us to get the value of B2 as 20 minus 7.5, which is equal to 12.5. So therefore, B2 is 12.5. And of course, B1 is simple. B1 is just simply the whole thing, so 25. And we use the formula half B1 plus B2 times H in order to get the area under the graph. The height, of course, is the Y value of the maximum point. So the height of this trapezoid would simply be the Y value here. And this Y value is approximately 3.3, actually exactly 3.3 from the Y axis here. And this is why we used 3.3 for H. And substituting all the values into the equation gives us a total distance of 62 meters. Figure 1.2 shows the axes of a speed time graph for a different object. The object has an initial speed of 50 and decelerates uniformly at 0.35 meters per second for 100 seconds. Draw on figure 1.2 the graph to represent the motion of the object. So it has an initial speed of 50. So therefore, we have to start the graph at 50 when the time is 0. We start from this point here. Decelerates uniformly. This tells us that the slope has two properties. It's negative because it decelerates, so the acceleration is negative, and it's constant. So that tells us that this is a straight line, not a curve. So we want to draw a constant line moving downwards, of course, downsloping. And we want to get the final speed, of course. So how do we get the final speed? We use the equation V equals U plus AT. The final speed is V. This is equal to the initial speed, which is 50, plus negative 0.35, which is the acceleration, because the deceleration is 0.35, times 100 seconds, which is the time. So we get 50 minus 35, and that gives us 15 meters per second. So how would we use the final speed? Simply by saying that we have a final point of 115. So 100 for X and 15 for Y. So somewhere in the middle between 10 and 20. That would be somewhere here. So this is our final point, 115, like this. And we simply join the two graphs, the 2 points, excuse me, in one straight line. Next, we are required to calculate the distance traveled by the object from 0 to 100. Like we said before, the distance, if it's a speed time graph, so we have AVX again, we are at V, and we want to get X, so we're moving up the stairs, so we get the area. So distance is going to equal area. We want to get the area of this shape. Of course, this shape is also a trapezoid like the last problem. But here, interestingly enough, the bases are vertical because the base does not have to be horizontal. The base has to be the two parallel sides of the trapezoid. So this would be B1 and this would be B2. And the height in this case is the line joining the two bases. So that would be not the diagonal, of course, not the blue line, but the horizontal line here would be the height. So let's write down the formula again. The distance is the area. The area is half B1 plus B2 times H. And then let's proceed to substitute each value in the equation. So B1 is the height of this line here, which is 15. So we put 15 for B1. And then for B2, this would be the height of the other side, which is 50. So we put 50 here. Finally, the height is the horizontal distance between them, which would be the 100. And we put 100 underneath the H like this. So we have half times 65 times 100. These would give us 32.5. So the final answer would be 3250 meters. Let's check the written answer and confirm. So the correct answer is 3,250 meters. You can always approximate to two significant figures, and you can write the answer as 3,300, but both of these are correct answers for this question. Figure 1.1 shows the speed time graph for the motion of a car. The mass of the car is 1,200. Calculate for the first 20 seconds of motion the distance traveled by the car. So again, we have a speed time graph, and we want distance traveled. So from V to X, up the stairs, you're getting the area. And we want to get the area under the graph between 0 and 20. So let's just draw a line here at 20. And we are required to get the area of this triangle here. So the area of any triangle is half times base times height. The base is the horizontal side here, so we can substitute that with 20. And then the height would be the vertical side. And it seems that the vertical side is somewhere between 10 and 15. So let's draw the horizontal line like this and count the boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 boxes between 10 and 15. So each two boxes count for 1. So this would be 11, and then this would be 12, and our required point would be 13. So this would be point 20 and 13. Therefore, the height here is 13, and the total area is half times 20 times 13, which gives us 130 meters. Next, we are required to find the acceleration of the car. The acceleration in this case would be the slope, because just like we went up for X, we'll go down to get A, and down means slope. M is the letter that represents the slope. So let's get the slope between 2 points. We have 0.00 and we have 2013. We can simply do 13 minus 0 over 20 minus 0. And that would be the acceleration of the car, which would be roughly 0.65 meters per second squared. Triple I requires the resultant force acting on the car. This is a bit out of scope, but we'll do it anyway. So we have a rule that says F equals ma, where F is the net force or the resultant force, and the mass is 1,200, and the acceleration is 0.65. So all we have to do here is simply multiply them together. 1,200 times 0.65. I will use my calculator. And the final answer would be 780 newtons, because the unit for force is newtons. So 780 newtons would be the final answer. Now for B, we are required to describe the motion of the car in the period of time from 25 to 40. So we're just qualitatively describing, and we said before that a frowning curve represents decreasing slope. And the slope here is the acceleration. So therefore, decreasing acceleration would be the correct answer here. So we write down decreasing acceleration. Let's check the written answers. So the area is 130 meters, as we got. And it seems that the acceleration is 0.65 as well. Let me clear my writing, make things clearer. So 130 is correct, 0.65. Here we multiply and we get 780. And finally, we say decreasing acceleration. Of course, you can say speed is increasing at a decreasing rate, but this sounds too complicated. Decreasing acceleration would be the correct answer here. Figure 1.1 shows a rocket-powered sled traveling along a straight track. The sled is used to test components before they are sent into space. Figure 1.2 is the speed time graph for the sled from time t equals 0. Mark a point labeled P to indicate a time when the acceleration of the sled is not constant. So we said that the slope is not constant when the graph is a curve. So the acceleration here is the slope. And we want a part of the graph where the slope is not constant. So it cannot be linear. So it has to be somewhere where the graph is very obviously curved. Maybe somewhere like this point here. So we can just mark point P in this place. Calculate the acceleration at t equals 1. So we can calculate the acceleration at t equals 1 because this part is linear. So the acceleration again is the slope, like we said. And at t equals 1, we can get the slope because the graph is a line. We have 2 points here, 0, 0, and 1 with this point here. So we have 5 boxes covering 200 in speed. So each box covers 40. So we have 5 boxes. So 200 divided by 5 gives us 40. So 40, 80, 120. Therefore, you have 1 and 120 as the second point, and you can proceed to calculate the slope. 120 minus 0 over 1 minus 0. This gives us 120 meters per second. So per second squared, excuse me. So the acceleration here would be 120 meters per second squared. Determine the distance traveled by the sled between t equals 1 and t equals 2. So let's get the points again. This point here we said is 1 and 120. And this point here would be 2 and 240, because we said that each box accounts for 40. And this is one box above the 200, if you can see here. It's exactly one box above, so it would be 240. Now we want to get the area of this shape. So this shape is a trapezoid, like we said before. And this is B1, this is B2, this is the height. You can immediately write them down. B1 equals 120, B2 equals 240, and the height equals to 1. So the area is half 120 plus 240 times 1, half B1 plus B2 times H. So 360 inside the bracket, and you multiply by half, you get 180. Therefore, the distance traveled is 180 meters. C requires the resultant force, C says that the resultant force acting on the sled remains constant during the test. Suggest why the acceleration of the sled is not constant. So this is a suggest question. A suggest question requires creativity. It's not something necessarily strictly within your curriculum. It's just something that you need to think about. Normally, the force, the resultant force, is equal to mass times acceleration. So if the resultant force is constant, why is it possible that the acceleration is not constant? Even though normally mass is constant. But the only way that acceleration is not constant if the force is constant, the force is constant and the acceleration is changing, then the mass has to change as well. So does that make sense in this particular problem? Yes, it does, because in this case, this is something moving into space. This is a rocket-powered sled, and it is projected into space by burning fuel. So when it burns fuel, the mass inside it changes because the fuel is gone. So the mass of fuel decreases, right? So therefore, since the mass decreases, the acceleration will change as well. Let's look at the written answers now. And they seem to be consistent with what we said, and the mass decreases because the fuel is used up. A comet traveling in space enters the atmosphere of a planet. Figure 1.1 is the speed time graph. During the period from t equals 0 to t equals 6, both the speed of the comet and the velocity of the comet remain constant. State what this suggests about the motion of the comet. So let's just look at the answers and run a brief explanation on each because we're repeating the same concepts again. So if the speed and the velocity both remain constant, what is the difference between speed and velocity? Velocity has two components, magnitude, which is speed. This is the magnitude, and direction. So if the speed is constant and the velocity is constant, what does that tell us? That the direction must be constant as well. So therefore, there is no change in direction. In double I, we are required to find the distance traveled from 0 to 6 in the period t equals 0 to t equals 6. So where is t equals 6 on the graph? 6 will be halfway between 4 and 8. So let's count the boxes between 4 and 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 boxes and we want 6, which is halfway in between. So we count 5 boxes and we draw a vertical line up. So the base here is 6. This is a rectangle, of course, and the height is this distance here. And of course, this distance is 4 boxes below 40,000, which would tell us that the height is 36,000. Because we have 10 boxes from 30 to 40, so each box is worth 1, and it's 6 boxes up or 4 boxes down. So therefore, it's 36,000. So all you have to do is simply multiply 6 by 36,000, and that gives us the area or the distance. We can convert it to kilometers by simply crossing out 3 zeros because we divide by 1,000. Next, we are required to discuss what the graph shows about the motion of the comet during the period t equals 6 to t equals 10. So what do we know about the graph here from 6 to 10? So from 6 to 10, what happens to the slope? Is it constant? No, the slope here has two properties. It's frowning and it's negative. So we have two properties here. The slope is negative because the line is moving downwards, and it's concave down as well. So it's frowning. So what does this tell us? Negative means that it decelerates. But it's not constant deceleration. Due to the concavity, it's decelerating more and more with passing time. So the idea is that it's frowning and negative. So if it's frowning and negative, this is actually increasing deceleration. How is this increasing deceleration? Let's look at the slope. So let's look at the slope at this point here versus, for example, the slope at this point here. What is the difference? Which one of these is steeper? Of course, this one here is steeper. So the slope as a magnitude, as a number, is increasing, but it's increasing in the negative. So therefore, we say that the deceleration is increasing. Finally, in question C, we are required to determine the acceleration of the comet at t equals 11. So how do we determine the acceleration at t equals 11? First, we count the squares from 8 to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we seem to have 10 squares between 8 and 12. So we have 4 seconds and 10 boxes. So how much does each box represent? Each box represents 4 over 10, which is 0.4. And we want at 11. So where would 11 be? So we can just simply increment by 0.4. So we have here 8.4, 8.8, 9.2, 9.6, 10, 10.4, 10.8 here. Finally, we have 11 at this box here. So we want the slope at this very weird point. I meant to show you how tedious it is just to help you understand what's going on. So 11 is in a very weird place. So how do we get the slope at 11? Do we need the point where the time is 11? We really don't. How come? Because the point at which time is 11, which is this point I'm shading in blue right now, belongs to a straight line. And a straight line has constant slope. So we don't really have to use the point where the time is 11 to get the slope. Remember, we want the acceleration, so we want the slope. We want the slope when the time is 11. We don't really have to use the point where the time is actually 11 because it belongs to this line that I shaded in blue. So we can just take the initial point and the final point in terms of x and y, and we can use them to calculate the slope. And this is what I'm going to do. I'm just going to call this x1, x2, y1, y2, and we'll do y2 minus y1 over x2 minus x1 to get the slope. So therefore, we have 19,000 minus 12,000 divided by 10.8 minus 12, or the other way around, it doesn't matter. So you get 7,000 in the numerator divided by negative 1.2 in the denominator. And as the written answer suggests, this gives us negative 5,833 meters per second squared. Of course, you can approximate the two significant figures, and you get 5,800 meters per second squared for the acceleration, in the negative, of course. Suggest what happens to the comet at t equals 12. At t equals 12, something very strange happens in the graph. You see a vertical line falling downwards, and the speed suddenly becomes 0. So what does that suggest? A collision of sorts. So the comet stops. How would that happen? When would that happen? If it hits the surface of a planet, for example. Moving on. A car accelerates from rest at time t equals 0 to its maximum speed. Figure 1.1 is the speed time graph. The mass of the car is 2,300. For the time between t equals 0 and t equals 5, determine the acceleration of the car. So this is a repetition. Let's briefly look at the answer. In order to get the acceleration, we need to get the slope of the graph. So in order to get the slope of the graph, we need to take 2 points. Of course, this is a linear section. So we simply take 0, 0 and 5, 15, and we calculate the slope as I did here. And the slope is 3 meters per second squared. Next, we need the resultant force. And we said before that the resultant force is obtained by F equals ma. So you multiply the mass by the acceleration that we got in the previous problem. And this gives us 6,900 newtons. In B, we're required to describe the motion of the car between 10 and 15. And we explain how the figure shows this. So of course, here it's concave down. And since it's concave down, it's frowning. And that tells us that the slope is decreasing. So we have decreasing acceleration because the slope here is acceleration. So we have decreasing acceleration due to the positive and concave down slope. Between t equals 10 and t equals 5, the force exerted on the car remains constant. Suggest and explain why the car moves in the way shown by figure 1.1. So if the force exerted on the car due to the engine is constant and the acceleration is not constant, that tells us what? It tells us that the net force is not constant. So remember, the net force is equal to mass times acceleration. This is changing. How do we know that this is changing? From the graph. The graph tells us that it's a curve, it's concave down, and we said that the acceleration is decreasing. So how does this matter? Why does this matter? Because the mass of the car is constant. So the net force must be changing. What is the net force equal to? This is, again, slightly outside of the scope of this video, but the net force will be the driving force minus the resisting force. So they tell us that this guy is constant, but the net force is changing. So why could this happen? How could this happen? Only if the resistance is changing. So why would the resistance change? Because air resistance is affected by speed. The greater the speed, the greater the air resistance. And this is a very important concept. So as speed increases, air resistance increases, and therefore the net force decreases, which is why the acceleration changes. You don't really have to say that, but you have to show that you understand that it is due to air resistance and that air resistance increases with the increase in speed. Figure 1.1 shows the speed time graph of a person on a journey. On the journey, he walks and then waits for a bus. He then travels by bus. He gets off the bus and waits for 2 minutes. He then walks again. His journey takes 74 minutes. For the whole journey, calculate the distance traveled and the average speed. So let's look at the written answer and discuss together. We said before that if we have a speed time graph, the distance is the area. I'm sure you memorized this by now. So we need to get the area under the graph, and we have here 3 rectangles. So the first rectangle has a base of 20 and a height of 5. So therefore we have 20 times 5, but bear in mind that the speed here is in kilometers per hour, whereas the time is in minutes. So we have to divide by 60. So we have 20 times 5 over 60 for the first rectangle. For the second rectangle, the base is also 20 again. And the height is 40. So again, we have to multiply 20 by 40, but we have to divide the answer by 60. Finally, for the third box, you have to realize that it begins at this point and ends at this point. So you need the value of one small box. So from 70 to 80, you have 5 boxes. And this gives you 10 minutes. So one box has to give you 2 minutes. So therefore, the first box gives you 2 minutes, which is 52. And the final box gives you 74. So therefore, you have 74 minus 52 multiplied by the height. And the height, again, you have to count the boxes. 1, 2, 3, 4, 5, 6. And you multiply by 6 and divide by 60 again. So therefore, you get 100 plus 800 plus 132. This is 100. This is 800. And this is 132, all divided by 60, of course. If you add them up, you will get 17.2 kilometers. How would we get the average speed? The average speed is the total distance divided by the total time. We already have the total distance, which is 17.2 kilometers. And the total time, as we said, is 74. This is the final point on the graph. We have to divide it by 60 to account for hours. So therefore, 17.2 divided by 74 divided by 60 would give you 14 kilometers per hour. State and explain Which feature of a speed time graph shows acceleration? The feature is the slope. Of course, we said the slope or the gradient. And the slope expresses acceleration because it's the rate of change of y with respect to x. Remember, the slope is what? y2 minus y1 over x2 minus x1. So it's the change in y over the change in x. Here, the change in y is the change in v. The change in x is the change in t. So therefore, v over t, in a sense, or change in v over change in t, gives you the change in speed, which is acceleration. So therefore, the slope of a speed time graph is the acceleration. Finally, state and explain the acceleration of the person at time t equals 40. Of course, at time t equals 40, you have a horizontal line, so the speed is constant. And therefore, since the speed is constant, we deduce that the acceleration is 0. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.